logarithms and logarithmic functions. In order to understand logarithms, we're first going to look at the exponential function f of x equals to 2 to the x power. Making a table, we're going to plug in our base 5 points. When I do negative 2, 2 to the negative 2 power is going to be 1/4. Negative 1, I get 1/2. 2 to the 0 power gives us 1. 2 to the 1 power gives us 2. And 2 to the second power will give us 4. Remember that we have a horizontal asymptote at 0. We have a plus 0 on the outside. I take my points and I plot them. Draw the graph. There's the graph of f of x equals to 2x. Identifying its domain. As I work all the way across, it will always be touching the graph. So I have a domain of all real numbers. I check the range. It doesn't start touching it until after that horizontal asymptote. So my y values or my f of x values will be strictly greater than 0. Now, one thing that we have focused on in Algebra 2 this year is finding inverses. And the one thing that we learned about finding inverses is that we're just trading x for y and y for x. So I make a new table. My x value now becomes y. My y value now becomes x. And I go ahead and do that for all of my ordered pairs. And I'm going to take that table and I'm going to graph it. But before I graph it though, what's the inverse of a horizontal asymptote? Well, the opposite of horizontal is vertical. So I'll now have a vertical asymptote that goes through 0. And I plot my points. Draw my graph. There's the inverse graph of 2 to the x power, or just an exponential function in general. I could even check its domain. Now, when I check the domain as I work across, this time it doesn't start touching the graph until I get past the vertical asymptote. So my domain in this case are going to be x values that are greater than 0. Now that I check the range, as soon as I start working up, it's already touching it, and it will always be touching it as I work up. So the range in this case is all real numbers, which makes sense because if I have x values as domains and my y values of range, if I trade the domain with the range, then you can see that I'm just trading the domain and the range down underneath. So that's what a logarithm function looks like. Now that we understand what a logarithm is, we need to have some notation for it. Right now I have an exponential here. You might have seen on your calculator before that you had an log button. That is a logarithm button. Now, if I want to convert something from exponential form to a logarithmic form, here's how it follows. I'm going to drop the base down. So whatever my base is in an exponential is going to be my base for a log. So I'll say log base b. What it is equal to, the x is now going to come over to the log. And I'm going to take the exponent. That's going to be what it's equal to. So essentially, even though a log might look complicated, all a logarithm is it simply tells you what the exponent should be. Now let's convert some examples here. We're going to rewrite 15 to the third power equal to 3,375 into logarithmic form. If I follow the arrows that I had on the previous slide, I'm going to drop the base, have log base 15. The answer, 3,375, is now going to come over to the log side. And the exponent of a 3 is what it's going to be equal to. So log base 15 of 3,375 is equal to 3. So what this is saying is 15 to the what power is 3,375? It's 3. Let's look at another example. 125 to the 1/3 power is equal to 5. I follow the same arrow system. Drop the base, so I have log base 125. The answer of 5 is going to come over to the log side, and the 1/3 power is going to be what it's equal to. So log base 125 of 5 is 1/3. That's converting from exponential form to logarithmic form. We'd also like to go from logarithmic form back to exponential form. And lucky for you, you can follow the same arrow system. So if I know that my base here is a 2, I can still bring the base down. The answer 3, what it's equal to, is going to come back over to be the exponent. And the 8 in the log is going to be on the other side. So log base 2 of 8 is 3. That's saying 2 to the third power is 8. One more example. Log base 4 of 1 over 256 is equal to negative 4. Follow the arrows, drop the base, bring over the negative 4, and the 1 over 256 will now become the answer. So now we've gone from exponential form to logarithmic. Now we've gone from logarithmic to exponential. And we're going to use that here to evaluate some logarithmic expressions. Now I've got log base 16 of 4. And you might say, well, can't I just type that into my calculator? Unfortunately, you can't, because most calculators have the log programmed with a different type of base than what's usually in the example. So here's what we're going to do. Step 1, this technically is a number even though there's a bunch of letters in it. I'm going to set this equal to y. Now that I have that, I'm going to convert it into an exponential form. So I follow my arrows. Drop the base, bring over the y to an exponent, and the 4 is now going to be on the other side. Now previously we've already solved some exponential equations, and one of the things about an exponential equation is that our bases have to be the same. So can I write 16 in a way that I use 4 as a base? And I can. 16 is the same thing as 4 to the second power. Now that I both have same bases, I can multiply or distribute that exponent on top to get 4 to the 2y power equal to 4 to the 1 power, meaning that if there's not an exponent with the 4, it's automatically a 1. Now that I have both of the bases to be the same, I can block them out, worry about just my exponents, and solve the equation that says 2y equals 1. Divide both sides by 2. Now we got y equals 1/2. Another example. Log base 1/2 of 256. If you remember from the previous slide, I went ahead and set the log equal to y for my variable. And then in step 2, I converted it back to exponential form. Now the fraction, you may remember that I also have my cross the line change to sign. So the exponent of the 2 on the bottom of the fraction is a positive 1, but when I cross the line change the sign, it now becomes 2 to the negative 1 power. Again, I still don't have the same bases, so I'm going to rewrite 256 with the base of 2. 256 is 2 to the 8th power. Now I have two bases that are the same. I can start simplifying from there. Distribute my exponent on the left, block out the bases, and I'm going to solve the equation that says negative y equals 8. Now that's negative y, so I'm going to divide by negative 1 to get y equal to negative 8.